Yeah. Hi, everyone. I'm Martin, and this is my teammate, Harrison. We're working on bridge component recognition through cutting plane trained conditional random fields. This is our problem. So we are given an input of 3D mesh models. And look, here's the 3D mesh model of a bridge. So these different colors represent different components. So what we want to do is try to recognize all these components. This data can be like synthetic models, which are like CAD models. And they can also be like 3D mesh models recovered from 3D point cloud. So in that case, it has like application for like reconstructing the beam models for different structures. And notice that we don't have any texture or RGB information, so that we cannot apply traditional techniques on this. And also, like, because this is essentially a multi-class classification problems, and we would very want to try deep network on this. Unfortunately, we don't have this much data because like 3D mesh models are very hard to obtain. So yeah, so given all this like object or different component in this bridge, how can we like recognize them? So the features we need extracted are not only the like features of the object themselves, but also its location or its functions. Another observation is that we have really complicated connectivity in our data set. This is an image of the bridge, like underneath the deck. So you see a lot of thin structures. It's really a complicated connection. This poses a challenge for us, but at the same time, it provides a cue for us to solve the problem. Therefore, contextual modeling is required. So what we do is to model our like mesh models as graphs. We treat each the like objects on the left and as like each individual node or vertex in the graph. And we can extract the physical connectivities, which defines this neighborhood relationship. And this altogether gives us a graph. And on the right this is a node connectivity graph. And this is the simplified version. So on average, a bridge has like 4 times the number of nodes as presented here. Once we have a graph, it is very like easy to model it with conditional random fields. I'm using a different notation here as what we have covered in class. The FPQ are the nodes, which are the X in our lecture, and FPFQ are the corresponding labels, which are the Y in our lecture. We have a unary potentials plus the binary potentials. The binary potential is the potentials that captures this like a pairwise interaction, which is a contextual information. Notice that this pairwise potential is different from the smoothing price typically used in image segmentation or image denoising. So once we have the CI formulation, we train it with structure SVM. The structure SVM is a large margin method for structured data. So it is extension to the classic SVM we have encountered in class. It treats the entire graph as a single input instance instead of each individual node. So to train the structure SVM, all we need to do is to provide an oracle that solves this loss-augmented inference problem, and which is the original testing problems plus the loss function. This is actually one of the benefits of structure SVM because it allows us to pick any loss function we want. So we pick this to be 1 minus accuracy because accuracy is the value that we benchmark our algorithm on or evaluate our algorithm. So the good thing is that we can directly optimize over the values that we evaluate on for our algorithms. And this is the result. We have 25 bridges of 5 categories. We picked 20 of them as training instances. When tested on the rest, you can see here we reached an accuracy of 68.9%. And this is not very high, but we showed improvement over the ones without contextual information. You see there's still a lot of confusion right here, so we still need to improve our algorithms. And that's all I want to say, and thank you for listening.
Okay, thank you. Quick question. Yeah. What was the state of the art before you did this?
We actually didn't find any previous work on classification of 3D mesh models.
Okay, good, thanks.
Yeah.
Okay, Nick, please stop.